Yo, what is up, guys? Welcome back. We got another episode today. I didn't end up coming back till today. I literally got back like less than an hour ago. So, um, yeah, we missed 2 days, so it's okay. I was out of town, but we're gonna take a look at I think episode 82 today. So looks like we got Magneton here. Let's take a look at the sound. What? Okay, that was so weird. Hang on. Let me lock in. Let me lock in for this sound. I didn't even know how to do it. It's like that's how Magneton sound. That was kind of cringe, but whoops. That was kind of cringe, but that's all right. Yeah, let's take a look at our Leetcode of the day now. I did actually do a couple problems yesterday. I actually did the problem of the day yesterday. Looks like this is actually a pretty decent problem. Put marbles in bags. I don't know if I want to attempt it, because I don't feel like super comfortable with heap problems yet. Yes, I do know what a heap is, but I want to feel comfortable on these problems. So I think what we got to do today is, we're pretty far through this. We've been taking a look at greedy problems. We have a few DFS, BFS, and then we're getting into some search trees. I kind of do want to get into the graphs. It looks like here they do have some graphs, which use DFS and BFS, and we got the heap priority queue here. Do want to take a look at these problems, some binary search problems. I'm okay with them. I get the intuition that the problem is binary search, but it's hard for me to implement it in different ways because I'm not really 100% comfortable with it yet. But I do want to start getting into some of these DP problems. I feel like we really have to start pushing and getting into a little bit of these problems to feel a little bit more comfortable with a broad range of problems. So yeah, what we'll do is we'll open our powerful study program. Some DP problems, got some grid problems. I do want to go through these sorting and searching ones. I think it's important to revisit some of these basic sorting algorithms. I think what we'll do is we'll do one DFS, we'll do one binary tree, we'll finish this BFS problem, we'll take a look at a graph problem, and then I think, we'll take a look at this problem, we'll do the DFS problem. We have done this one before, part sum 3. This is a tough binary search DFS problem. I remember having trouble with this one. Take a look at the lowest common ancestor. So we'll do this one. We will take a look at a graph, take a look at a priority queue, and then maybe we might take a look at a greedy problem. Yeah, and we'll see kind of where we're at with time. I'm hoping that'll probably be around an hour and a half. I am a little bit short on time. I kind of want to finish this probably around 12 o'clock. There's a few things I got to do today. I got to go to the grocery store, do laundry, and then I got work from 2 to 7. So, I don't know, a little bit of chores to do today. But yeah, anyway, let's get into it. Let's take a look at this problem here. So we have solved this problem. I believe it was recently, March 17th. Yeah, so it was about 2 weeks ago. Given the root of a binary tree, the level of its root is 1, the level of its children is 2, and so on. Return the smallest level x such that the sum of all the values from those x is maximal. So level 1, we got 1. Level 2, we got 7. Level 3, we got 7 plus -1. So return the level with the maximum sum of, which is 2. Is this really a DFS problem? Okay, we're doing the BFS problem. Okay. I think that problem's a bit too easy. Let's do this one here, because we did solve this one recently. I think this is a little bit of a tougher problem here. We did this about a week ago, so Given a binary tree, find the lowest common ancestor of the given two nodes. According to the definition of LCA on Wikipedia, the lowest common ancestor is defined between the two nodes P and Q, as the lowest node in T has both P and Q as descendants, where we allow a node to be a descendant of itself. Okay. This is a very tough problem. I do remember looking at this one a week ago. The lowest common ancestor is defined between the two nodes P and Q. So we got P and Q, we got 5 and 1. Right, so we're looking at the lowest common ancestor of this one. Ancestor between 5 and Q is 3. 0, 1, 2, 3. Are we returning the level here? I think. So we got 5 and 4. We're returning 5. Oh, wait, hang on. Okay, the lowest common ancestor, which is 3 here. Looking for the lowest common ancestor of nodes between 1 and 3. Oh, 1 and 5, sorry. 1 and 5, so the lowest common ancestor here would be 3. Do I remember how I solved this problem? No, but I do remember kind of keeping track of the grandparent. I think this is definitely probably a recursive problem. The LCA of nodes 5 and 4 is 5, since a node can be descendant of itself, according to the LCA. Got 5 and 4. Okay. Trying to think how we'd solve this problem. So, To be honest, I really don't remember solving this problem a couple week ago, whatever it was. I do believe I solved this with recursion, so I'm not. Lowest common ancestor of a binary tree. Give me some hints. See, maybe if I can implement it with some hints. Here's some hints to help you solve. Recursive approach. Okay, yeah. Left and right subtrees. If both P and Q are found in the different subtree nodes, that node is the LCA. Post-order traversal logic. Post-order would be left-right root, I believe. I'm just going to make sure with that post-order traversal. Left-right root. Left subtree, then right subtree, then finally the root. Yeah, okay. So pre-order does the root first, so root left-right, so post-order is left-right root. Check the left and then the right children first and process the current node. 3 possible cases. If P and Q are found in different subtrees, the current node is the LCA. Okay, we do have a recursive approach here. We want to pass in our current node, right? What are we returning? We are returning the values, so I guess we can make a res array to return the value, right? P and Q will exist in the tree, so I think we're fine with 0. Okay, well, we know if we hit a an empty node, we just want to return, right? So that's obvious. That's a simple base case, right? Now, what do we know? How do we know that if it's a common ancestor? Well, I guess if we find... If you find P or Q, return that node. Okay. Yes. If node dot val is equal to p, or node dot val is equal to q, we want to return this node, right? I guess this is another base case, right? Think about what happens when you traverse a tree recursively. I mean, yeah, we're going this node, this node, this node, back to this node. So we traverse here. We get here. Check the left and right children first, then process the current node. Interesting. You have to check the left and right children first. Why? Why do we have to check the left and right children first? Well, checking the left and right children, we're looping all the way to the end. Okay, I think we have to check the left and right children first is because we're looping. We want to start from the bottom. So if we check the left and right children first, we get to the bottom, then we return back up, right? Okay, so we check left and right children first. Alright, so we do node.left is equal to DFS node. Node.right is equal to DFS node. So, okay, sorry, my bad. We have to check. Okay, we're doing the base cases first, and then we're checking. Well, oops. If not node, return. Looking at a base case. Okay, we check the children. Then whoops, this should be node.left here. Node.right. I guess we can name this left so we can easily reference this left. Because we want to reference the node underneath it when we get to that node, whatever we return. So if left and right, well, if left is equal to a, yeah, think about, well, if left and right, we want to return the node. Otherwise, we just return left if left, else right. Okay, so we go through the bottom, we come back up, right? And if left and right, we return the node. So if we have a value, otherwise we return left, if left, else right. We need P and Q in here. PQ. PQ. Okay, then we want to return res. Or res is equal to DFS root PQ. Expected 3, output null. Oh, I guess we can just return. Then we just want to go, well, we don't need the res then, I feel like. What are we returning here? Tree node, okay. No, darkness will be okay. Okay. Because they can be no.val unique. Right, return node. returns this. This one checks, well, if it's in the left. Left, right. If left and right, return node. It's definitely a tough problem. Like, it's hard for me to think about this problem. Right? Look, I understand, like, okay, let's pass through this, right? So we got p is equal to 5, q is equal to 1. So this is our thing, right? We go 3. We go, okay, or we skip all this. We go to the left of 3, right? Defense on the left, p, q, right? So we go 5, right? If not, no. If base case, if node is equal to p or node, we return the node, right? So we return node 5, right? To our left function. Then we call our right function, we return node 1, right? When we return node 1 and do if left and right, then we know that this is our thing. So we return 3, right? This one here, we look through, we go, well, we want to find 5 and 4. So we go through here, right? Node to the left, we found 5, so we return, right? We check, well, we see, well, if node is equal to p, we return that node, right? So we return 5, okay? Let's walk through this test case. We got. Okay, so that's how we get this one, right? And if we get, well, if left and right, we return the node. Just get left, we return left. If node is equal to p. Okay, I understand the code. It's just hard, like, it's hard to see that, you know, like it's hard. I feel like you have to have a really good understanding of recursive functions and DFS, right? Maybe I'm not there yet. I don't know, but let's continue anyway. Let's take a look. We return that. My internet is bad right now, dude. What's going on? Okay. All right. So we returned our DFS. Yep. Let's take a look at keys and rooms. Okay. This is a graph problem. This is our very first graph problem that we're attempting, which is definitely very interesting. So the n rooms labeled 0 and -1, and all the rooms are locked except for room 0. Okay. We pick up key 1. We can then visit room 1, then pick up key 2. We can then visit room 2, pick up key 3. We then visit room 3, pick up room... Since we were able to visit every room, so we return true. There are n rooms labeled from 0 to n-1. Your goal is to visit all the rooms. However, you cannot enter a locked room without having its key. When you visit a room, you may find a set of distinct keys in it. Each key has a number on it, denoting which room it unlocks, and you can take all of them with you to unlock the other rooms. Given an array of rooms where rooms I is a set of keys that you can obtain if you visit a room I. Return true if you can visit all the rooms, or false otherwise. Okay, this is definitely an interesting problem. This is considered a graph problem, right? Or a depth first search problem, but I actually am not really too sure how to implement DFS on an array. Now I'm thinking obviously it's probably the same way, but I'm curious. Right, so simply we need to iterate over this array, right? My intuition was thinking about using like some sort of hash map or something while iterating over this. We check, okay, what's in the hash map. We add it to our hash map. If we have that key, we can then move to the next value, right? I feel like somehow you can easily loop over this, right? I feel like somehow you could use some sort of like double for loop or something. Some O of n squared solution that can loop over this. Look inside the array, get the key, store the key somewhere in something, right? Maybe in some sort of hash map or something. Check if this is all values in rooms I are unique. Okay, so you can use a set, right, for O of 1 lookups, right? So loop over here, check this, what's in here, put it inside the hash map. And visit room 1, pick up key 2. Right, so we can easily check this room. We check what's in here. If this is equal to I, then we can move to the next one. And we can keep moving to each room. Every room we return true. That's what I'm thinking, but I'm sure... I feel like that is the brute force solution. But will the brute force solution return? Probably not. Right? I mean... Okay, so I was right. We use a set, right? Let's call our hashy is equal to set, right? Let's create our DFS function, right? Def DFS. We can check, well, do we want to pass anything in our DFS function? Not sure, man. Let's search this up. Utmost. To get this problem, I want to use the iterative approach, right? Okay. Which technically I think would be BFS, right? Let's start with a set. We create a queue. So from collections, import DQ, right? We get that. We create our queue. So we do queue is equal to DQ. And we want to put in our first value, right? DQ room 0. Okay, I'm just curious. Let me just print the queue, right? Kind of want to see what this looks like. Then we're going to do the actual DFS, right? DQ1, right? Then we do, well, while we have something in our queue, right, we want to pop, right? Room is equal to DQ, sorry, room is equal to q.pop left, right? So we pop it for key in rooms. I guess if key we would just want to add the key to our hash set, so we do, well, key.add, sorry, no, hash.add key, right? But we want to check, well, what are they doing here? While queue, right? I guess, sorry, we need to add in our room 0. While queue, we pop, we check, well, for key in rooms, key in rooms room. Right, so this is how we're checking the room. We're referencing the rooms array and we're checking, well, then we add the key. Right, so if key not in visited, we add this key, okay? And then we append the key. Q.append key, right? Okay. Then we would return if our visited, sorry, if our hashy return is it true if hashy is equal to our rooms, I think, right? Equal to rooms. Oh yeah. Else false. Whoops, we need, I think, a capital T here. Visited is not defined. Okay, whoops, we meant hashy. Okay, we are adding everything. Okay, we're comparing the length of visited to the length of rooms. Okay. Length of hashy equal to the length of rooms. Not true, false. Okay. Are we missing anything else? Well, maybe, are we adding this wrong? Okay. Why did that just work? I have no idea. Why is this wrong? There's hashing a queue with the keys found in room 0, but you forgot to add room 0 itself to hashy. This can cause incorrect results if room 0 is not revisited in the BFS traversal. Okay, our expected result is true. All rooms can be visited. Your code's execution hash is equal to 1 keys from room 0, but room 0 is missing. Walk me through this test case. Okay. Print 0. Okay. We have the set 0. Alright, so we have 0 DQ while Q. Room is equal to Q dot pop left. For key in room 0. Okay. Right, that's how we start from room 1. But we're adding this extra 1 because we have the empty list over here. Okay. I understand. Interesting problem. Okay. That's the BFS solution. Obviously, we have the queue, right? We're looping through each value within the array, processing each thing, right? Keys in room's room. If key not in hash, you add the key, right? Obviously, this is a simple iterative BFS approach where we have the while and then we have the for. Instead, really, in our tree traversal, this pop left is usually inside the for loop because we're popping those elements right inside the for because we want to check each node. So that is one difference for sure, but I think everything else is pretty similar. In BFS tree in iterative BFS tree traversal. Okay. So now, I mean, this here is a DFS problem, right? So how would we implement DFS here? Well, can this problem be solved with iterative DFS? Okay, right, so, well, it'd probably be the same thing, right? We'd have our stack, right? We'd have our hashy, right? Okay. obviously want to pass in our first value, right? So we have 0 inside of here. Okay. We'd want to loop through our stack. So while stack has something in it, we probably want to pop from the stack. So stack.pop. Let's do like, I don't know. Room is equal to stack.pop. Okay. We loop through, we want to do, well, for room in rooms, room, right? I think okay, this is key, yeah. Key in rooms room. I want to do, well, if key not in hashy, then we want to append, well, hashy dot append key hashy dot we append hashy, and then we want to append our stack dot append the stack dot append, oh shit man, what is it, the key as well, right? Then we're going to return, I think that would be it, right? Then we return true if the length of hashy is equal to the length of our stack. Okay, we need the else false. We'll always forget the else false. List indices must be integers or slices, not a list. We passing in oh. I meant to just put in 0 here, I think that's why. I think I just submitted by accident. Ah! No, I didn't. Okay. False, false. Okay, let's print out hashy. I can print us our rooms. Okay, it's because we're comparing to the stack. This is meant to be rooms. I am so hungry, man. Okay, nice. There we go. Very similar approach with a DFS solution using a stack, right? Just kind of want to get to know the difference, right? Let's just like view a random. I did this one yesterday. Let's see, what do we use here? We used recursive function here. I think we did recursive yesterday too. Yeah. Do we ever submit a iterative one? Jesus, man. Like, here we go. Yeah, same thing. We pop, and then we, compare, add the if left, if right. So again, very similar the approach. I'm trying to think now, like, now how can we do this recursively? That is a very good question. Def DFS, right? So we need to pass in something. Well, I'm, 'cause, 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 ' Do we need to pass in our hashy function? I don't know. Right, we have passing out rooms maybe. Okay. What would be our base case here if we did this with a recursive function? I think maybe we pass in room. Well, I guess our base case would be, okay, like if our room is greater than the length of rooms, right? Then we can just, well, might as well return none, right? I think. Okay, then I think, well, we somehow have to loop, so we go like for room in rooms. Sorry, for key in rooms, room. Yes, if key not in hashy. Let's do recursion DFS, right? If key not in hashy, and we do key dot append. I was pretty close, I would say. I was pretty close, right? We have an empty set. Ow. Maybe we don't need this, right? Key dot append hashy. Then we call our function here, DFS key, right? We call our DFS 0, right, on our first room. Then we return, well, if the length of our return true if length of hashy is equal to length of nums, length of, sorry, rooms, else false. Variable key where it's not associated with a value. Oh my gosh, whoops. Hashy dot add dot append room. No attribute append, right? We need an add. Always forget that. Okay, nice. This is definitely an interesting problem. Definitely learned a lot. I actually think these problems a lot are going to help me with my recursion thinking, which I think is what I need. I mean, I just need to keep doing problems. Definitely a good problem. I do like those problems. I forgot what we were going to do next. You know, maybe we might... Maybe we might leave the heap priority queue for a little later and focus on the graphs, I'm thinking. And then we really kind of go ham into that. So let's take a look at the BFS problem, and then I think we'll probably call it, right? Okay, geez. So this is definitely a trickier problem. I don't know if we're ready for that. Let's take a look at rotting oranges. Maybe that one's... Okay. I don't really want a grid. I kind of just want a... I don't really want a 2D array. I kind of want kind of an adjacency list, if you want to call it. But I think we'll try and implement it anyway, right? I feel like you're given an m times n grid where each cell can have one of the three values. 0 representing an empty cell, 1 representing a fresh orange, or 2 representing a rotten orange. Okay. Every minute, any fresh orange that is forward directionally adjacent to a rotten orange becomes rotten. Return the minimum number of minutes that must elapse until no cells have a fresh orange. This is possible. Return -1. Okay. We got a rotten orange here. Right. We got an empty one. Orange, 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 orange. Minute 1. Okay, so every minute, any fresh orange that is forward directionally adjacent to a rotten orange becomes rotten. Okay, right, so this one becomes rotten, this one becomes rotten. And then the next minute, this one becomes rotten. And this one becomes rotten. And the next minute, this one becomes rotten. This one becomes rotten. Okay, I understand. I feel like eventually these matrix problems are going to come my way, so I got to get better with them. Again, I'm not good with two-dimensional arrays yet, I feel like. But, you know, I feel like it's important to learn, you know. So we do have to use BFS here. So I'm obviously going to go, well, from collections, import DQ, right? To think about this problem... Right, obviously, return the minimum number of minutes that must elapse until no cell has a fresh orange, right? Well, when we're using BFS, we're traversing level by level. So... I'm trying to think, do we go level by level? So like this here would be a maximum of 2, right? Then we go, well, 1, 2. Or 1, 2. So really the output would be, okay, how's the output 4? Well, we would go 1, 1, 2, 3, 4. Okay. $9.94 running on. BFS is ideal for shortest path problems. Okay. Okay, let's think about this, right? So the first step here is that we have to identify all the raw oranges and store them in a queue, right? So we did import, right? Okay, let's print our rows. Let's kind of visualize this. We print our rows. Okay, how will we print our rows? What do we do? Well, our rows would be the length of the grid, right? And I feel like our column would be grid 0. Okay, right, so we would do, well, rows equal to the length of grid. Cols is equal to the length of grid 0. Okay. I'm going to create our queue equal to dq. I don't think we need to pass anything in originally, right? Because we're going to add everything to the queue, right? So reduce. Put all bottom oranges in queue, right? So how would we do that? Okay, so we've got to loop through this for loop. So we go, well, for, how do we loop over a 2D matrix? We would go, well, for rows, right? Okay, for R in range rows, for C in range cols. Okay, if rows columns, what is rotten, is equal to 2, right? Or if, sorry, grid, yeah, you know, reference grid. If grid RC is equal to 2, then we append if grid RC is equal to 2, we want to append our fresh orange. So we go, well, q dot append what will we append? We must append the grid, right? Grid RC. Yeah, we don't want to append the actual value, we want to append the indice, right? Okay, right? I guess we probably want to keep our fresh count, right? Because we want to compare what our original fresh count was to our thing. So I guess else if grid RC, sorry, grid, yeah, RC is equal to 1, right? Because we can skip 0. It doesn't really matter. We don't really need the empty cell because we're not doing anything with it. I guess we can keep some sort of like value here. So let's call it fresh oranges is equal to 0, right? Then we just want to increment, well, fresh oranges plus equal to 1, right? Hashtag 2, we want to check, well, hashtag 2, loop through using BFS and make all oranges bottom, right? So, well, I guess we do the same thing, but we need to do while Q, right? We would loop through, well, for R in range rows, for C in range cols. We would check, well, okay, obviously no, we somehow make our directions, well, right, left, down, up. Okay, so we make some sort of directions array here. Directions is equal to, it's an array that stores, okay, well, assume this is going north, so 0, 1. Right, this goes south, 0, -1. 0, -1, right? Then this goes west. And then this one goes, this goes east. Yeah, -1, 0, right? Right. Okay, so obviously I was wrong. Right, left, down, up. Right, that should have been self-explanatory here. Well, I feel like this is the row. If the row is 0, the column is 1. So this is row, col, min, right? So we'd want to, well, q dot pop left, right? We want to pop row, col, minute is equal to q dot pop left, right? Then we need some sort of for. So for dr, dc, direction row, direction column, and directions. And R and C is equal to R plus DRC plus DC. Okay, so we're checking each direction, right? For DR and DC, okay. For DR, DC in directions, right? We're checking every direction, okay? So, DR plus R, new row, new column is equal to, so let's just do it simple. New row is equal to dr plus our original row, and then dc is equal to dr plus our original column. All right, so we can go up, left, right, down, right? We're checking each direction, okay? Which is what we need to do in the problem. I didn't really think about that. I was just kind of thinking about looking at the problem, right? Because we don't know technically, right? We don't know, well, there could be one left, up, down, whatever, right? Because technically we could, one of our oranges could be here, right? So when we do that, right, we want to somehow loop through and check all the directions, right? So for, well, we check, well, if 0 is less than or equal to NR is greater than rho. So we're checking if it's in bounds, right? So if 0 is less than or equal to NR or less than rows, and 0 is less than or equal to NC is less than cols, right? Which is our original values, right? That we created up here, right? So we're checking our bounds. So this checks if we're within our row and we're within our column. And then we need to check, well, if our grid NC DC is equal to 1, which is a fresh orange, then what do we want to do, right? Well, we technically want to append to our queue, right? So we do q.append. We'd append our NC, our DC, and then increase our minute by 1, right? Sorry, NRDC, that's what I meant. NRDC, right? We need the double here, right? Okay. So how do we know? Well, I forgot this, right? So how would we know if all our elements are done, right? So if we see one, if this is a fresh orange, right? Then we increase our we need to somehow keep count of our, I guess, well, no, we just make, well, grid NR DC is equal to 2, which is a rotten orange, right? Then we decrease our fresh oranges minus or equal to 1, right? So we've done that. Then what would we return outside of here, outside of our while, right? So once we get through our queue, we would return, well, we would return time. Oh, do we need some sort of max time variable, right? Where are we updating our time? Okay, here we go. Go here. We got update our time, right? To get our max time. So time is equal to max time minute, right? We would return time if fresh oranges is equal to 0, right? Else -1, which I think is correct. Yes. Invalid syntax. NRDC is equal to 2. Sorry, I'm checking if it's equal. We need to assign it. Invalid syntax. Grid NRDC is equal to 2. Oh, whoops, we got the colon there. Don't want the colon. Can't access local variable time where it's not associated with a value. Oh shit, we didn't initialize it, right? We need to initialize our time is equal to 0. NC is not defined. NC, new column, new row. New column, new row. That's what I meant. We got DR. We want DC here. I can't actually look at variable fresh oranges. Okay, I misspelled it. Fresh oranges. Fresh oranges. Okay. NRDC. This needs to be NC. NC, not DC. NR, NC, NR, NC, NR, NC, NR. God, man, how am I so bad at this? NR, NC. Why are we returning -1 here? I think I have some misspelt variable here. NC and calls RC. Yeah. Okay, this is meant to be row. This is meant to be call. There we go. Okay. It was a good problem. I do understand kind of how we did that. It was cool to kind of think about the 2D matrices there. Yeah, I did learn a lot on that problem. So that was a good problem. Maybe we can take a look. Well, see, they don't really have any graph practice, right? They learn topological sort last time. Learn different graph structures such as BFS, TFS. Learn minimum spanning trees and their different algorithms. Learn shortest paths and its algorithms. Leetcode, like playlist for graphs. Graphs. Okay, here we go. Jeez, man, this is a lot of fucking graphs, dude. Minimum spanning trees, strongly connected graphs. I did learn about a bunch of these in college. I know I'm familiar, obviously, BFS, DFS, Dijkstra's. I learned topological sort, prims, Kruskal's. I think Floyd Warshall pops in my head. I'm not 100% sure. I feel like graphs is fucking big, man. It's a big, like... The graphs boot camp. Oh my god, dude. 2-hour videos, dude. Jeez, man. Like, it's a lot to watch, bro. Can't solve graph questions. How to study graphs.
Hello and welcome. My name is William. Today I want to bring to you my complete video course on graph.
Experience is...
Guy has a course on graphs, man. Jeez. Yeah, I'm starting thinking graphs are a lot bigger than what I thought. Okay, yeah, BFS, yep, I know BFS. Dijkstra's algorithm, union find, random spanning trees. Okay, we'll save this. I'll save this as a favorite here. Yeah, we'll keep going through our list. Our Leetcode 75 list. Obviously feeling pretty confident with these ones here. Gonna finish these. Probably I'll finish off these ones tomorrow. Maybe we'll take a look at Pass on 3 again. Continue doing this. I do want to get into doing a little bit of heap priority queue, so it's going to be kind of a lot of learning. Doing the problems, like obviously, probably a lot of these, I don't have the intuition yet to be able to solve it on top of my head, but hopefully as we continue, we can learn. Yeah. Tough problems for sure. Getting some DP problems, backtracking. Yeah. Mine's user code. Yeah, we're getting some backtracking. We are making good progress though. I mean, I'm happy to start touching on BFS and DFS. But yeah, we still have a lot to go. So anyway, appreciate you guys watching. I'll see you guys in tomorrow's episode. See you later.